Listen carefully. Scientists have measured how fast the universe is expanding. They did it in two different ways. Both methods are trusted. Both are precise. But they give two different answers. And if both are correct, then something about our universe is very wrong. Let's slow this down and make the problem very clear. Imagine you're standing on the side of a highway watching cars pass by. You use one radar gun to measure their speed. It says the cars are moving at 60 miles per hour. Now imagine someone else, standing a little farther down the road, uses a different radar gun. Their device says the same cars are moving at 73 miles per hour. Both radar guns are modern. Both are calibrated. Both have been tested many times. So now you have a problem. Are the cars actually moving at two different speeds? Of course not. That would make no sense. Which means one of three things must be true. Either one of the measurements is wrong, or both measurements are missing something, or the situation is more complicated than we thought. This is the exact situation scientists are facing with the universe. For nearly 100 years, astronomers have known that the universe is expanding. Galaxies are moving away from each other because space itself is stretching. The speed of that stretching is described by a number called the Hubble constant. This number is not just a detail. It affects how old the universe is, how big it is, and how it will evolve in the future. So measuring it correctly matters. Now here's where the tension begins. When scientists measure the expansion rate by looking far back in time, at the early universe, they get one value. When they measure it by looking nearby, at galaxies closer to us today, they get a different value. These measurements are not vague guesses. They come from different methods, different data, different instruments, and yet, they refuse to agree. The difference is large enough that it cannot be ignored. This disagreement is called the Hubble tension. And it's not just an argument about numbers. It's a sign that something about our understanding of the universe may be incomplete. Because the universe is only one thing. It cannot expand at two different rates at the same time. So, either one of our most trusted measurements is wrong, or the universe is telling us a deeper story we haven't understood yet. To understand why these measurements disagree, we need to look at how scientists measure the universe's expansion in the first place. And surprisingly, they don't all measure it the same way. One approach looks far back in time, very far. It studies light that has been traveling for billions of years, light that was released when the universe was still young. By examining this ancient light, scientists can reconstruct what the universe was like shortly after the Big Bang. They can measure how dense it was, how hot it was, and how fast it should be expanding today if the laws of physics haven't changed. Think of it like finding a baby photo and predicting how tall someone should be as an adult. That's one method. The second approach looks at the universe much closer to home. It measures distances to nearby galaxies. It uses stars that pulse in a predictable way, and exploding stars that act like cosmic distance markers. By measuring how bright these objects appear, scientists can calculate how far away they are. Then they compare that distance to how fast the galaxies are moving away. This method doesn't rely on the early universe at all. It measures expansion directly, right now. So here's the crucial point. These two methods are completely independent. They use different data, different assumptions, different parts of the universe. Which is why, at first, scientists weren't worried when the numbers didn't perfectly match. Small differences are expected. But as measurements improved, something strange happened. The gap didn't shrink, it grew. Each method became more precise, each reduced its uncertainty, and yet, the disagreement became harder to ignore. That's when cosmologists realized this wasn't just experimental noise. It was a real problem. Because if both methods are done correctly, they must lead to the same answer. Unless something fundamental is missing from our picture of the universe. At this point, a reasonable question comes up. What if the measurements are simply wrong? Science makes mistakes all the time. Instruments fail. Data gets misinterpreted. So it's fair to ask whether the Hubble tension is just a technical error. And for years, that's exactly what scientists assumed. They checked everything. They recalibrated instruments. They reanalyzed old data. They redesigned experiments from scratch. The early universe measurements were tested again and again. Different satellites, different detectors, different analysis methods. The result stayed the same. Then scientists turned to the nearby universe measurements. They checked the stars used as distance markers. They examined how dust might affect brightness. They tested whether assumptions about stellar behavior were flawed. Again, improvements were made. Uncertainties shrank. But the expansion rate didn't move toward the early universe value. It stayed stubbornly higher. This is the key reason the tension became serious. If only one method disagreed, scientists would dismiss it. If the disagreement were small, they would average it out. But neither of those things happened. Instead, two independent methods, using different physics and different parts of the universe, became more precise and more different. That is the opposite of what random error looks like. In science, errors tend to fade as measurements improve. They don't harden. So when cosmologists say the Hubble tension is real, they don't mean it's mysterious. They mean it has survived every obvious explanation, which leaves only uncomfortable possibilities. Either both methods share a hidden flaw we haven't identified yet, or the universe is not behaving the way our current models expect it to. And that's when a measurement problem becomes a theory problem. To understand one possible explanation for the Hubble tension, we need to talk about something surprisingly simple: where we are. Most cosmological models assume that, on large scales, the universe looks roughly the same everywhere. That assumption is called cosmic uniformity. It doesn't mean matter is evenly spread out, galaxies form clusters and filaments, but it means no region of the universe should be fundamentally special, no center, no edge, no privileged location. But what if that assumption is slightly wrong? What if our region of the universe is different from average? Imagine you're standing inside a large valley. If you look outward from the bottom of the valley, everything around you appears to slope upward. But if you were standing on a flat plain, the same landscape would look very different. Your position changes what you measure. Some scientists have proposed that we might live inside a cosmic void, a vast region of space with slightly lower density than the universe around it. Not empty, just less crowded. If that's true, it would have an important consequence. Matter outside the void would be pulling outward more strongly than matter inside. From our point of view, galaxies nearby would appear to be moving away faster than they really are. Expansion would look faster locally. But when we measure the universe using the early universe method, which averages over much larger scales, we wouldn't see that local effect. The result? Two measurements, two answers. Not because the universe is broken, but because our perspective is biased. This idea doesn't require new physics. It doesn't change the laws of gravity. It simply changes where we think we're standing. Of course, there's a catch. For this explanation to work, the void would need to be enormous, hundreds of millions of light-years across, and we would need to be relatively close to its center. That's a strong claim, which is why scientists take it seriously, but cautiously. Because if we really are inside a giant cosmic bubble, then our location in the universe is more important than we ever assumed. So is the cosmic void explanation actually correct? The honest answer is maybe. There are observations that support it. When scientists map the distribution of galaxies around us, they do find that our local region appears slightly underdense. Not dramatically empty, but less crowded than average. Some surveys suggest this underdensity extends across a very large volume of space, large enough that it could affect local expansion measurements. And when researchers plug these kinds of voids into their models, something interesting happens. The local expansion rate increases, not all the way to match the nearby universe measurements, but enough to reduce the tension. That's important, because it shows the idea isn't just philosophical, it makes testable predictions. But there are also serious problems. For the void explanation to fully solve the Hubble tension, the void would need to be enormous, hundreds of millions of light-years wide, and we would need to be located suspiciously close to its center. That creates a new problem. Cosmology is built on the idea that our position in the universe is not special. We don't live at the center of anything. So, proposing that we just happen to sit near the center of a giant cosmic bubble feels uncomfortable. Not impossible, but statistically unlikely. There's another issue. Other observations, like the cosmic microwave background and large-scale galaxy flows, place limits on how extreme such a void can be. Too large, and it would leave signatures we should already have seen. So the void hypothesis sits in an uneasy place. It explains part of the problem, but not all of it, which leaves scientists in a familiar position, with an idea that works just well enough to be tempting and just poorly enough to remain unproven. If the cosmic void explanation can't fully resolve the Hubble tension, then scientists are forced to consider a more unsettling possibility. What if the problem isn't where we are? What if the problem is our theory? Modern cosmology rests on a set of assumptions about what the universe is made of and how it behaves. We assume dark matter exists and interacts only through gravity. We assume dark energy is constant over time. And we assume the laws of physics worked the same way in the early universe as they do now. The Hubble tension challenges those assumptions. One possibility is that dark energy is not constant. If dark energy behaved differently in the early universe, it could change how expansion unfolds over time. Another possibility is that there are additional particles or fields we haven't accounted for. Subtle changes in the early universe could alter how fast expansion appears today. There are even ideas suggesting that gravity itself may behave slightly differently on the largest scales. None of these ideas are fringe. They are explored in mainstream research. But here's the crucial point. All of these explanations come with a cost. They add complexity. They require changing models that have worked extremely well in every other test. So scientists are cautious. They don't introduce new physics lightly. They look for the simplest explanation that fits all the data. And right now, no single explanation does. The Hubble tension may be telling us that something small is missing. Or it may be hinting at a deeper revision of our understanding of the universe. Either way, it's not a mistake to be ignored. It's a message waiting to be understood. So what happens next? When scientists encounter a problem like the Hubble tension, they don't rush to conclusions. They gather more evidence. Right now, new telescopes and surveys are focused on measuring the universe's expansion in independent ways. Gravitational lensing, where massive objects bend light, offers one path forward. So do precise measurements of galaxy motions across vast regions of space. Each new method acts like a tiebreaker. If they agree with the nearby universe measurements, the case for new physics strengthens. If they agree with the early universe value, then something is wrong with how we measure distances locally. And if they land somewhere in between, then the story becomes even more interesting. What matters is that this is not a dead end. It's an active investigation, one where data, not speculation, will decide the outcome. This is how science moves forward, not by clinging to old ideas and not by discarding them carelessly, but by letting evidence slowly force change. The Hubble tension may eventually fade, or it may become the first crack in a much deeper revision of cosmology. Either way, the universe is doing what it has always done. It's reminding us that we don't yet understand everything, and that the most important discoveries often begin with numbers that refuse to agree.